is, as you can see, I'm a little bit behind, but I plan on playing catch up today. We're going to dive into day 11 and see if we can knock this thing out. We got about, but not feeling so great, so I'm a little bit behind, but it's okay. I think we can power through this one. All right, day 11, cosmic expansion. You continue following signs for hot springs and eventually come across an observatory. The elf within turns out to be a researcher studying cosmic expansion using the giant telescope here. He doesn't know anything about the missing machine parts. He's only visiting for this research project. However, he confirms that the hot springs are the next closest area likely to have people. He'll even take you straight there once he's done with today's observation analysis. Maybe you can help him with the analysis to speed things up. The researcher has collected a bunch of data and compiled the data into a single giant image, which is your puzzle input. The image includes empty spaces and galaxies. For example, the researcher is trying to figure out the sum of the lengths of the shortest path between every pair of galaxies. However, there's a catch. The universe expanded in the time it took the light from those galaxies to reach the observatory. Due to something involving gravitational effects, only some expand. In fact, the result is that any row or column that contains no galaxy should all actually be twice as big. Okay, so they got arrows here indicating which ones. So they would expand out twice. These rows and columns need to be twice as big. The result of cosmic expansion, therefore, looks like this. Equipped with the expanded universe, the shortest path between every pair of galaxies can be found. It can help to assign every galaxy a unique number. In these 9 galaxies, there are 36 pairs. So that's 9 times 8. To calculate the pairs, right? 9 times 8. It's 72. 9 times 8 divided by 2. Yeah, divided by 2. So that's your number of pairs. Only count each pair once. Order within the pair does not matter. For each pair, find the shortest path between the 2 galaxies using only steps that move up, down, left, or right. Exactly 1 or at a time. The shortest path between 2 galaxies is allowed to pass through another galaxy. For example, here's one of the shortest paths between galaxy 5 and 9. Okay, so technically, because we're not going angles here, the shortest path is always going to be stepping to it or going down and over or over and down. So we can, for instance, we can go with 5 as 2, 3, 4, and then straight down 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4. Yeah, because you don't count that step you're on. So that's 8 plus the final step is 9. So that's 9 spaces away. You can also do that this way as well, or you could stair step it down. The reason why this is important is because it becomes simple as far as mathematically is concerned. We can take the x and y from here, do some x and y subtraction here, grab the absolute values, and that is the distance between them, x plus y distance. So the path has like 9 because it takes a minimum of 9 steps, blah, blah, blah. Okay, here's some other examples. This example, after expanding the universe, the sum of the shortest paths between all 36 pairs. So we're going to have 36 answers is 374. So expand the universe, then find the length of the shortest path between every pair of galaxies. What is the sum of these lengths? Okay, so I think just kind of running through some of these and know that they sort of try to lead you down a wrong path. Not intentionally, but kind of intentionally when it talks about expanding the universe. I don't think that that's necessary. I think what would make sense to me is that we can loop through this and we can count anytime we find a X position. If we're going down and we find an X position that is supposed to be scaled, we scale it. And the same thing when we're going right to left, we find a Y position that needs to be scaled, we scale it. I think we can look at doing that in these 36 pairs. So the other thing is that if we start at 1, right, and we calculate the distance to 2, 3, 4, 5, 6, 7, 8, 9. We don't need to calculate distance between 3 and 1 because we already have it. We don't need to calculate distance between 2 and 1. We already have that because I think 36 paths between the pairs, right? And so, but we don't have to do that. So just kind of keep that in mind that as we calculate a distance set between two, that kind of becomes the final distance. So we will calculate 1 to 2 and 1 to 4 individually, and 1 to 3 individually, 1 to 5, 1 to 6, etc. But then we're not going to calculate 2 back to 1. We'll calculate 2 to 3, 2 to 4, etc., and it'll get faster as we get through all the iterations. And then as far as the expanded universe, we'll just, as we hit one of those x's, instead of, we could expand it, but I have a feeling that might become a problem later, where when we cross over that threshold, if it's in our expanded set, then we could just expand that line and say, okay, instead of it just taking 1x, our scale, I guess, is 2. And then similarly for the y. So I guess the first thing is we're dealing with essentially a matrix. So, well, this is my default now, so that actually kind of makes sense. We want to get all of the xy's. So I'm just going to, and I was kind of upset with myself last time I worked with matrices. I'm going to create a point type. It's fine. Never mind. I'll probably be upset with myself again, but it's all right. For yes. If v equal that, then slice of int. All right, there we go. So now we got all of our galaxies. So let's see what we got out here. Yeah, I don't see an easy way, so I'm just going to have to do it myself, which is fine. That's the go way, I suppose. I guess we really don't need to predefine our pairs. So we know what our length should be. So our length of our pairs, pair length, should, I mean, we could just have this predefined. It should be the length of our galaxies times the length of our galaxies minus 1 divided by 2. And that should be our pair length. So, right. And then we'll say for length of pair length, or length of paths, we'll call it string to int, or length of paths is less than pair length. Cool. What we're going to do is we're going to loop over our galaxies, and we're going to calculate all of the lengths for the paths that we don't have until we reach the total number of paths, and then we can calculate. So the first thing is, how do we get into each one? Well, we can simply loop through our galaxies for galaxy in range of galaxies. And then inside here, we can say for to galaxy in range of galaxies. And then If I equal j, we can continue. So that's if our to galaxy and our from galaxy are matching. Then what we want to do is we want to say, hey, do we have a path? Instead of recording the index of the slice, I'm just going to record the index of the XY in the galaxy set. So we know that if we get the min between I and j, what we're going to do, and then we're going to do the max for the same. We're going to check, we'll just call this key. It'll be a little bit nicer, funct.sprintf. %pound or %d, %d. We'll make it look kind of nice. That's our key, and that's going to be our min to our max. So that way we always know that whatever the min and max of the index is, it's always going to be in that order. So it guarantees that our key is always going to be in that order so that we don't recalculate something we don't need to. So if path of key All right, so what we're saying is if the key is not found in our paths, then we need to calculate it. Otherwise, we already have it, so nothing to do. So if not okay, then we need to calc it. So path of key equal to calc distance. And this will be, we'll say, galaxy to galaxy. And then there's one other piece in here that is important, which is the expanded galaxies, or expanded space, we'll call it. All right, so I did not yet calculate the expanded space, which is somewhat important. What is this? Oh, okay, that's better. Yeah, we don't need the math one, which means we don't need to use floats. So I feel better about that. And then calc distance, we'll explain that function. So typically what it would be is the absolute of x minus galaxy sub 0 minus to galaxy sub 0 plus the same thing for the y, right? So that would be the 1 and 1. And that would be it. But because we have these expanded galaxy we have to handle, we have to first find them, we have to then provide them, and then calculate based on that. So how do we get the expanded galaxies? So for every row, we're going to loop through every character, and we're going to set expanded equals false. And then in here, actually we'll call it true. And if we hit this, then expanded equals false. And we can actually break out of here if that condition is true. And then we'll say if expanded, then we want to catalog this row, this X row as expanded, So the way we're going to do that is, how do we want to track this? What do we call this down here? Expanded space. I'm not really so worried about like memory and time complexity on this. Although we may change the data type if we need to in the future. But we'll call expanded space the map a string to bool or something. It doesn't really matter. And then so if expanded is true, then we're going to say expanded space sub, in this case, we're dealing with x, and then colon %d. So fun.sprintf. So we know this given row is expanded. And then we'll call that like that and that. Okay, perfect. So then similarly, we need to do the same, but in the opposite direction. So for each record, yeah, so this is not what I want. We'll get rid of that for a second. All right. So we'll iterate through each of the first records, and then we want to iterate through each row. So that should be fine. And then it really is, it's just better to do it in this case of m sub y sub x. Yeah. So expanded is false, and then we break, and then if expanded true, sprintf y, okay, true. So we inverse the y and the x ranging so that it's going to go for every column, and then it's going to go down every single x value. Boom, 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 boom. And if we see any character, the expanded becomes true. So let's pull our test input in for a second. Let's not get too far ahead of ourselves. Our input is going to be this, not there, this here. So this is unexpanded. That's important. If we grab the wrong input, yeah, sure. So we'll call calc distance, and we're going to give it a slice of int and a map of string to bool. And we'll call this from to, and we'll call this expanded space, and then we'll return an int, I think, is what that takes. What's a galaxy? Oh, just a slice of int. Got it. So that's your x, y, and then we'll return 0. Okay, so let's run the test, but there's a couple things I want to do. I want to print from this. I want to our expanded space, and then I want to print our galaxies. All right, cool. So let's just run this test. And what should our answer be for this one? Our answer should be 374. Okay. why it's 10. Oh, because yeah, I know why. All right, so let's go back to our test input. Let me put some hard returns in here. And let's see what our result is now. Okay. I made 2 changes while I was on that call. I added the break inside here, which I intended to do initially, and I added the break inside here. That gives us our XYs, or I'm sorry, it gives us our expanded X's and expanded Y's, or expanded rows and expanded columns. And then I just wanted to print out the galaxies. So we can enumerate on those galaxies, and we can calculate their distance for the ones that we don't have. Like I said before, the distance is pretty straightforward if we don't have to deal with this expanded issue. And in fact, if I went through and I expanded all the space first, I could just do this, but something tells me that it's going to get more complicated than this in part 2. So I don't want to do that. So instead, we're going to calc the distance. And so we're going to take our galaxy, our 2 galaxy, and our expanded space. And we're going to set the distance in the path keys to that. So what's calc the distance do? So what we want to do is we want to start at our from galaxies X from, actually we want, the min of from sub 0 and to sub 0. So whatever the min is, and then we're going to go to the max of that. I think it's equal then. We'll look at it in a second. And we're going to increase by 1. And our distance is going to be 0. And we're going to return distance. So then what we want to do is we want to say if expanded space and how did I notate expanded space? If that's true, then we know we need to scale it by some value. And so it's going to be distance plus equal to 1 and distance plus equal to 1. So we're always going to add 1, and then we'll add an additional 1 based on a scale. And so I'm just going to add a scale value here, which equals 0 for now, 1, because we want to duplicate. So we always know we have 1 and we're going to duplicate. So that scale is always true for that. And then that's going to give us our X distance. And then we're just going to do the same for Y. So from 1, 1, and 1, 1, and I guess we can change this to Y, 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 Y. Okay. And that should be it. So yeah, this goes away because it's not needed. And then finally, there's the last piece. And if any of this fails, I'll go back and test individual pieces this time. But this example after expanding the universe is sum of the shortest paths. So it's the sum of the shortest paths. So for range of paths, yeah, we're just gonna we're gonna not do this, and we'll just transform it at the end. I really don't know why I chose to do that. Okay, so that's gonna be the combined path. So let's try it out. Let's go for broke. Undefined x. Okay, cool. Y. All right. 374, 446. Let's print paths. Let's see here. 0 to 1 is 8. Let's look at our examples here. So in this example, 0, which is 0, 3 to 1, 7. So 0, 0, 1, 2, 3 to 1, 7, this distance here. We don't have 1 and 2, we have 1 and 7. So let's look at 1 and 7. So 1 and 7 is 21 according to this. And it is 15 according to this. So why is it that much more? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So 21 is definitely wrong. So the scale is duplicate, so that should work. That should also work. It's additive, so it's just the down in the right. Let's stop here. Let's put a breakpoint. And let's do min equals 1 and max equals 7. Okay. I meant to step into that. All right, we're inside here. Distance is 0. And our x starts at 1. And we're going until 7. So we're at 3 because the expanded space, and we're on line 3. Okay. So our distance should be from 1 to 7. Should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 14. See, 1 and 7 is 15. That's like 9 because there's a minimum of 9 steps to get from Galaxy 5 to Galaxy 9 to locations plus steps. So here are some other examples of shortest path lengths. 1 and 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. 11, 12, 13. I don't think you're right. I'm probably wrong. Probably wrong. Let's look at expanded twice. The rows and columns need to be twice as big. Oh, let's count. Sorry, let's count 1 and 7 from up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1, 2, 3, 4. That's 15. Okay. So we have 11. So I think that is because we are including one of these that we shouldn't. Okay. Right. Calc distance. Okay, our distance should now be 10. Okay, great. This might be it. Okay. Yep. All right, so I just had the one I was starting from and moving to. I had a slightly off, but we got it. So let's actually run this with our input. Awesome. Got that taken care of. Knocked out part 1. Let's check out part 2. Part 2. The galaxies are much older and thus much farther apart than the research initially estimated. Now, instead of the expansion you did before, make each empty row or column 1,000,000 times larger. That is, each empty row should be replaced with rows, and each empty column should be replaced with, in these examples, so 8410. If each rows or columns were nearly 100 times larger, the sum of the shortest path between each galaxy would be 8410. So, all right, obviously we're not going to get quickest time here. Never planned on it, but what we can do is this scale function here. We can add scale to this, and yeah. So we can pass scale in here, and then simply have scale as part of part 1. And so our initial scale will be 1, and then our second scale will be 1,000,000. And if we want to see this in test, we'll just call it scale int and int and scale 1, and then I might have to make one adjustment. But this just is simply test.scale. Okay. And now this should be fine as is. And then if we change our scale according to what they want here, example above each empty row or column nearly 10 times larger than the sum of the shortest path. So 10 and 1030. So we'll put 10 in here for our scale and 1030 for our test. Okay, and then so I think I know why that is. We're over our amount, and the reason is if we go back to here when we did the scale, we just did a plus additive, and really this should be we shouldn't be adding the distance because it's really not a scale at that point. Instead, we should be and the actual scale for the first one is now going to fail because the scale should be 2 on the first one. Yeah, which is what we want. And so then we could do the 100 example if we want, just to prove a point to myself or to whoever. And we'll run that. And again, so we're pretty confident that this will work as is. So if we, because of our approach here, let me get rid of these prints. Right. So put that in here. And we got it. Awesome. So we completed day 11. Great job. Go us. Just a brief recap. Part 1, pretty straightforward. We had to do some pre-parsing, but we had essentially a matrix or row column set of values, and anywhere there was a pound sign that indicated a galaxy. And then there was this concept of expanded space. So if you had any row or column that did not include anything, any galaxies, that could expand by some scale, initially double scale. And then we took that concept a step further. So we had to calculate that. And then once we calculated those, we had to go through all of the pairs. So the way that I did that is I know that we need a maximum set of paths for our pair length. And so I calculated that. I calculated the pair length by determining how many total galaxies we had divided by 2. And then we iterate through each of those, and we calculate anywhere the I and the J equals, we know we don't need that. And then also if we've already calculated the distance, we don't need that. And so as we calculate these different distances, eventually we'll get to a point where we'll have everything solved, and it's just math at that point. So the one major difference here is we are iterating through every iteration of X and Y so that we can do the math. Now, I'm not sure if it'd be more performant, but rather than looping through each X and Y, we could assume the total calc of X and Y, and then we can look for the intersection of 2 lines. And since these are, they're just bisections of each other, we should be able to, or intersections of each other, we should be able to do that pretty quickly. And then we can figure out how many intersections between sets of lines there are. I'm not sure if that would be more performant or not, but the solution was performant enough. So why add the additional complexity? So once we calculate the distance, the reason we expanded it, like I said before, is because we had this idea of scaled galaxies. And if we had pre-scaled the the matrix or the row column set, it would be infinitely much longer to process. So doing it this way, we have execution time in about a second. So that's relatively good. That's pretty much it all I have for today. If you have any questions, please leave them in the comments below. I try to be pretty responsive, even if it's not a Python specific, or sorry, a Golang specific question. If you want to ask something about Python, I have some Python experience in the past, although Go is my preferred language. But as always, over and out.